Hello, I welcome you all in this presentation related with the subject failure analysis and prevention, and we are talking about the fundamental sources of the failure under the failure analysis and prevention subject. We have talked about the two aspects related with the deficient design, and these were there in form of the presence of the stress razors, and the second one about which we have talked was about the imperfections in base metal. We will be talking about the few other aspects related with the deficient design, and these may be in form of upgrading of a part or system which had very successful record of the performance to the some more severe conditions for different application. So, upgrading of a part with good record of service, to a new application. This is one thing, or to the more severe service conditions. So, sometimes we are encouraged so much with the very good performance of some of the systems or the mechanical components that they are also recommended for the different application, for the different service conditions. So, which sometimes leads to the premature failure of the component, and the reason for this kind of the failure becomes maybe in the variety of forms. For that we can see that the deficiency in design of a component can be in various forms, like presence of stress razors, changing design without proper consideration, duplicating a successful design for more severe loading conditions. About this aspect we are going to talk. There is another aspect related with the deficient design about which we will be talking in this presentation, is design developed without full knowledge of the stress conditions due to inability to calculate the stresses properly, or due to the complexity of the geometry of the component which is to be designed, or inability to use the proper criteria for the designing. So, under the first one, where we have to consider upgrading of a part to the more severe conditions, this can lead to the failure of the component due to a range of the conditions. One is like the metal is unsuitable for a given application. Unsuitability of metal for new application. So, this is one. This may unsuitability may be in form of more severe wear conditions or more severe temperature conditions, like something had a good record for the room temperature conditions. If the same is used either for low temperature conditions like -20°C or high temperature conditions like 300°C, so the performance of the component may not be the same. Similarly, something had a very good record for performance under the normal ambient conditions, but if the same is placed under the conditions like seawater conditions, where both corrosion and erosion is severe, or some petrochemical industry, or some like in chemical industry where the corrosion is dominating. So, the performance may be very adversely affected, because the material which had very good record of the performance under the normal ambient condition may not be able to perform in the same way under the different service conditions for which it has not been, it does not have the required characteristics. So, it's not necessary that a product which is having very good record of the performance will also be showing the similar kind of performance for the newer applications. So, this is what we can see here, unsuitable metal of the component for new applications may be in form of high or low temperature kind of, or wear or corrosion or the mechanical performance. Like for one application where the toughness may not be important at room temperature, but the toughness becomes crucial under the low temperature conditions if the same is to be used. Now coming to the another point, like the heat treatment requirements. Especially this is true for the steels which are subjected to the heat treatment, like the quenching and tempering. So, quenching is done primarily for the hardening purpose and tempering is done to induce the required toughness. So, the combination of the strength and toughness can be realized, and this will be these properties will be corresponding to the particular temperature of the tempering. So, say steel is tempered at 400 degrees centigrade, and the steel which was quenched and tempered at 400 degrees centigrade had very good performance record. But if the same component is to be used under the temperature conditions of the 450 degrees centigrade during the service, then it will, during the service itself will be over tempered, and that will be leading to the degradation in the properties of the steel, softening of the steel, and which may deteriorate the mechanical performance, and so premature failure of the component can take place. So, this is one typical example where the improper heat treatment of the component, the composition may be suitable, but if the heat treatment is inappropriate for newer application, then it also can lead to the failure. Similarly, the stress relieving, if in one situation stress relieving may not be crucial, but for new application, if the stress concentration, if the loading conditions are more severe, then inappropriate stress relieving can also lead to the premature failure of the component. Then there may be size and shape requirements, size and shape requirement for the new service conditions are for new application. Like if earlier it was being used for carrying the load of the 150 kilonewton, but in the new service if it is to be subjected to the 200 kilonewton, then it will be experiencing the more severe stress conditions. So, the notches or the geometrical features which were present in the component might not have been that crucial, but under the more severe stress conditions, these notches and the stress ridges may become very crucial. So, the similar so in that case the notches and the geometrical features may require the different kind of the geometries and the locations in order to avoid their adverse effect on the performance. So, the size and shape requirements may be different for the newer service conditions, and if without doing that, without changing the size and shape for newer service where loading conditions are different, then also it can lead to the premature failure of the component. Similarly, then we have the complex stress field become crucial for the newer stress concentration. Sometimes, like if the component was being subjected to the tensile stresses, and in the newer application it finds that it is being subjected to the torsional stresses. So, tensile stresses are uniformly distributed across the cross section, but in case of the torsional loading conditions, the maximum stresses are found at the surface. So, the discontinuities which are present at the surface may be more crucial for the torsional loading and for the bending conditions as compared to the case when it is a simple stresses magnitude is uniform across the section. So, here while in case of the torsion, the stresses in the core or near the center is 0 or it is very less as compared to the case when tensile stresses, in case of tensile stresses they are uniform across the section. So, depending upon the type of stresses, severity of the stresses or complexity of the stresses, the different sizes and shapes may play a crucial role. So, the complex stress conditions for the newer application may also lead to the failure. So, the point is about complex stress field may be crucial for the new application, for new application. Then there is another point like the presence of the stress regions which were not that important, but these may be very crucial under the newer conditions because of the complex stress field or the more severe loading conditions. So, they need to be considered differently. Say for example, if there was a notch with the radius of like say 0.5 mm. So, this will be causing the more severe stress conditions as compared to the case when it had like say 1.5. So, under the low load conditions like 150 kilonewton it may be okay, but if the load magnitude is increased to the 250 kilonewton, then these stress results may become more crucial, and in that case it may require the different radius at the crack tip for avoiding the unnecessary too high stress concentration, so that the premature failure of the component can be avoided. So, presence of stress regions can be critical for more severe conditions as compared to the earlier service conditions. Now, in light of these points, we will be taking up one case study where the engineers encouraged with the very long and successful performance of the spring retainer cap for the automobile, which we can see here in this diagram. What this diagram shows, this is the spring which is used in case of opening and closing of the valves in IC engines, and this spring is retained with the help of this cap. So, this is the stress spring retainer cap, and this cap, the cross section of this cap can be seen how the this is the upper portion, and these are there are different levels in the cap which are used to accommodate these springs. So, spring remains under the spring will keep on, the retainer will always be under the loading due to the spring. And in this case we can see there are some junctions, the varying cross sections, and at the cross sections some the fillets are there. So, these fillets will be used for having the gradual change in the loading and gradual change in the stress distribution. So, but in this particular case the retainer cap for the retainer cap was which had a very good record of the performance. The retainer cap which had a very good record of the performance for the low capacity engine like say 4-cylinder engine, but when it was used with the 8-cylinder automobile during the qualification run itself, the retainer cap failed. So, retainer cap failed during the field trials or the qualification run of 8-cylinder automobile, and the cap broke before trial run of 200 hours at 4100 rpm to the 4600 rpm after 26 million cycles. So, this test simulates the continuous running of the engine for 200 hours at 140 miles per hour. And so, these were the service conditions. The retainer cap failed, and the cap was made of the made from the 16 mm cold drawn 101. This is a plain carbon steel having the 0.1% carbon, was made of the 101 carbon steel. This is AISI designation of the steel, and it was in annealed condition. So, the processes which were used for making the retainer cap were the forging and then trimming, followed by case hardening using the carbonitriding for 30 minutes at 843 and the oil quenching for the hardening purpose. And in order to induce the desired toughness and to avoid unnecessary development of the residual stresses, tampering was done at 260 degree centigrade. And through this case hardening heat treatment, the case depth was it was desired to harden the case up to the depth of 0.0 up to the depth of in a range of 0.0252 to 0.25 mm, so as to achieve the hardness of 86 HRB. So, the macroscopy of the broken cap showed that the fracture actually originated from the section where change in cross section was taking place, and which we can see here. This is the periphery along which the cross section change in cross section was taking place, and this arrowed zone showed this arrow shows the location where from it was triggered. A smooth region in this area shows the nucleation of the crack by the fatigue, and thereafter it has grown in this direction, and then sudden fracture zone is rugged, rough and irregular. So, all this area is corresponding to the sudden fracture zone, and the smooth zone shows the location where the crack propagated in fatigue manner. So, a smooth area on fracture surface is characteristic of the fatigue fracture, with the brightness at the arrow zone shows the location where from crack initiated. Regular rugged areas correspond to the final fracture, and there was no sign of the plastic deformation, which suggests that material had a good strength, but the crack nucleated in the high stress areas, and then it grown under grew under the influence of the fatigue loading, and then it failed catastrophically. Metallography also suggested the normal, the ferritic and perlitic structure with the dominance of the ferrite. So, the microscopy also did not show any issue related with the microstructure. So, to confirm whether the cap had required properties or not, chemical analysis was performed, and chemical analysis of the cap showed that it is the composition of the cap is corresponding to the AISI 101 with the percentage of the carbon 0.11 and the manganese percentage 0.48, and the microscopy of the case hardened depth showed that it was 0.2 mm, and the hardness was found in the range of 84, which is slightly below than the specified value of the 86 HRB. And the microstructure because it was of the low carbon steel, so it had the normal ferrite and perlitic structure as expected without any inclusion and the other abnormalities. So, this analysis showed that the fracture initiated and propagated by the fatigue, and before final fracture the crack grew at the crack grew at the junction where change in cross section was taking place. So, the crack nucleated at the fillet between the pilot and the flange, and no significant material and the manufacturing problem was found. So, in order to overcome this issue, because the location suggested that the crack nucleated and it grew from the fillet zone. So, obviously it was indicating that high stress concentration due to the somewhat limited fillet led to the nucleation and growth of the crack under the fatigue conditions easily, and that is why design of the cap fillet radius was increased from 0.5 to 1.2 mm for better stress distribution, which in turn increased the fillet, and this increased fillet radius also helped in the manufacturing, because it is more difficult to realize or to achieve the fine radius as compared to the bigger radius, and this correction led to the successful performance of the retainer cap subsequently. Now, we will be talking about the other aspects related with the deficiency in design. So, this one about which we have talked, like upgrading of a part a part to new application, for which in this particular case inappropriate fillet radius led to the failure. There can be number of reasons for the failure when a part is upgraded to the new application, because the part is not designed for that application. Now, the second aspect is that the design criteria. You see, whenever the component is design of a part or component for an application. So, whenever the design is made, what we consider? We consider the service conditions, which for the mechanical design are primarily in terms of the load, like the type of the load, magnitude of the load, and then service environment, like in form of the temperature or corrosion. So, all these need to be considered when we are talking about the design to be developed for a given applications. But many times due to the improper calculation of the improper stresses for the design purpose, means that if the design is based on the improper stress criteria, then it can lead to the failure. We try to find out the service conditions effectively, so that we are aware of the type of the load, load in terms of the type of load, magnitude, and the service conditions. But sometimes we find it really difficult to have the kind of stresses which are to be used properly, and this can arise due to the two types of situations, in that improper stresses are being used for the design purpose. This can arise from the two causes. One is incorrect estimation of the load. So, basically the components, parts, machines, systems we used as earth moving machines, or the excavators, or the mining equipments, which can be subjected to the varying load conditions. So, in those conditions it becomes really difficult to correctly estimate the kind of load which will be acting during the service. So, incorrect estimation of the load during the service, and its the type and magnitude, all these can be leading to the improper stress criteria, or the improper stress is being used for the design purpose. And sometimes it becomes difficult to calculate, inability to calculate the stresses which will be acting on the component, So, sometimes the geometries of few components are so complex that they make it difficult to properly determine, calculate the kind of stresses which will be acting onto the component. So, improper estimation of the load and inability to calculate the stresses accurately for a given service conditions due to the complexity of the geometry of the component. So, these two situations will be leading to the use of improper stress, and if the design is based on the incorrect stresses, then of course it will provide the easy source for the failure of the component, because the section size and the shape of the component, all those will not be proper. So, continuing with this one, if we really do not know what kind of the service conditions are there, we are not able to estimate the load properly, and we are not able to calculate the stresses properly, then this can lead to the improper design of the component. So, apart from the improper design of the component, there can be another issue, like whatever the metal is being selected, metal selection for a given application, So, on what basis the material should be selected for the given application? We know that each metal will have certain mechanical, physical properties, like say the metal A may be of the high sigma y value and the low percentage elongation, and the metal B may be very low sigma y value, but the high percentage elongation. So, and likewise there can be very wide ranges, like the titanium alloys may have the strength of 1800 MPa. On the other hand, our simple mild steel may have like say 350 to 500 MPa. So, there can be lot of variation in terms of the strength that they offer, in terms of the toughness and the ductility that they offer. So, what we should consider for the design purpose, on what basis a given material should be selected, and for that purpose basically we need to consider the expected failure mechanism, expected failure mechanism. You know, the whatever component will be made, that will be put into the use. So, during the application, according to the service conditions, we need to estimate, we need to predict, we need to identify in which way the component can fail. The failure of component say can occur due to the ductile fracture, brittle fracture, ductile fracture where lot of elongation and deformation will be taking place, brittle fracture where without any change in cross section or change in the size and shape of the component, certainly the fracture will be taking place, or the component will be subjected to the high temperature. So, the change in dimensions will be taking place due to the creep, or the component will be subjected to the fluctuating loads. So, here it will be subjected to the fatigue, or the component will be put into the use, means component will be subjected to the corrosion. So, likewise there can be different situations, there can be wear in variety of forms like abrasion, erosion, cavitation, etc. So, there can be variety of ways by which the failure of a metal can take place during the service. So, that failure mechanism, expected failure mechanism is to be identified, and accordingly we need to see how a material should be selected and which kind of material should be selected for successful performance in a given application. Design and design actually helps to find out the suitable size and shape, but what parameter is to be used for determining that size and shape, that will depend upon the expected failure mechanism, whether it will fail by ductile, brittle, creep, ductile fracture, brittle fracture, creep, fatigue, corrosion or wear. So, coming to this one, if the component, say if the component is expected to fail by the plastic deformation at room temperature, then we will be considering the yield strength. If the component is expected to fail the deformation by at a high temperature, then we need to consider the creep rate or the creep behavior of the material. Similarly, if the failure of the component is expected to occur under the overload fracture, fluctuating load fracture or impact load conditions, then we have to consider the ultimate strength or the endurance limit or the endurance strength or the impact strength of the material. So, these are, so as per the case we have to consider the suitable kind of the parameters which should be used for selection of the suitable material. Now, coming to the few failure mechanisms and the parameter which is to be considered for, and this table basically shows the parameters that needs to be that should be considered for selection of the suitable material and suitable design. So, if the ductile fracture is taking place, if the estimated failure mechanism is the ductile fracture, then the yield strength as per the type of load, it may be tension, compression. Then if the expected failure mechanism is the brittle fracture, then we need to consider the fracture toughness, notch toughness, ductility, ductile to brittle transition temperature, so that the material can perform and its design can be based on these parameters and so that it can perform the intended function successfully in order to avoid any premature failure. So, if the failure has taken place, then we need to see what kind of force would have been the mechanism of the failure, and whether the material had these characteristics or not to resist those service conditions. So, this list can also be used to see what kind of characteristics a metal should have to perform under given service conditions. So, after the failure, we can easily identify the kind of failure mechanism which would be there for a metal, and if the material is material which has failed is having those characteristics or not, that can be used to identify if the design was proper or the design was deficient. So, the fatigue fracture, like if the design is to be based on the fatigue, if the expected failure mechanism is a fatigue, then the endurance limit and the fatigue strength with the stress ratios and the hardness should be considered. Thermal fatigue is the probable case for the failure, then the ductility and the peak plastic strain under the given temperature variations should be considered. If the creep is the foreseeable mechanism, then the creep rate at a given temperature needs to be considered, and for the plastic deformation, if the change in dimension of the component under the given service conditions is the possible way by which the component can fail, then we need to consider the yield strength, or at high temperature it is the creep. And if the component is subject to the tensile stresses in corrosive environment, then we need to consider the K1 SSC, which is the critical stress concentration factor under the corrosive environmental conditions, and the corrosion resistance to the specific environment also needs to be considered. So, now I will conclude this presentation. In this presentation, I have talked about the how upgrading a part to the newer applications can lead to the failure, and also I have talked about how the inappropriate design criteria and the improper stresses can lead to the failure. Thank you for your attention.